Good day, everyone. I am ArjinelR Caballero from BSE 3B Mathematics of NUST San Isidro Campus. In this video, I am going to explain the Eulers Theorem. But before we proceed to our main topic, let me share you a quotation about mathematics that William Paul Thurston once said. Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding. Now, let us talk about the person behind the Eulers Theorem. He is no other than Sir Leonhard Euler. Leonhard Euler was a Swiss mathematician, physicist, astronomer, geographer, logician, and engineer who founded the studies of graph theory and topology, and made pioneering and influential discoveries in many other branches of mathematics, such as analytic number theory, complex analysis, and infinitesimal calculus. He was born on 15th of April 1707 at Basel, Switzerland. He had 6 children and 2 spouses. His life was ended on September 18, 1783 at St. Petersburg, Russia. In number theory, Euler's Theorem, also known as the Fermat-Euler Theorem or Euler-Tauschent Theorem, states that if n and a are coprime positive integers and phi of n is Euler's Tauschent function, then a raised to the power of p of n is congruent to 1 modulo n. That is, a raised to phi of n is equal to 1 mod n. In 1736, Leonhard Euler published a proof of Fermat's Euler theorem, stated by Fermat without proof, which is the restriction of Euler's theorem to the case where n is a prime number. Subsequently, Euler presented other proofs of the theorem, culminating with his paper of 1763, in which he proved a generalization to the case where n is not prime. The converse of Euler's theorem is also true. If the above congruence is true, then a and n must be coprime. For better understanding, let's have this. If n is a positive integer, then the phi of n is defined to be the number of positive integers not exceeding to n that are relatively prime to n. Here are the rules in solving the phi of a function. Rule number 1. If p is a prime number, then phi of p is equal to p minus 1. For instance, solve for the phi of 29. Since 29 is a prime number, we use the formula phi of p equals to p minus 1. Substitute 29 to the p, so we have phi of 29 is equal to 29 minus 1. The answer is 28, therefore, the phi of 29 is 28. Rule number 2. If a equals p raised to n is a prime number, then phi of p raised to n equals p raised to n minus p raised to n minus 1, where p is prime number and n is equal to integer. For example, solve for the phi of 25. Since the phi of 25 can be written as phi of 25 equals phi of 5 squared, we can use the formula phi of p raised to n equals p raised to n minus p raised to n minus 1. We have phi of 25 equals phi of 5 squared. 5 squared minus 5 raised to 2 minus 1, we have 20. Therefore, the phi of 25 is 20. Rule number 3. If m and n are coprime and has the GCD of 1, then phi of mn equals phi of m multiplied by phi of n. Let's solve for the phi of 21. Phi of 21 can be written as phi of 21 equals phi of 7 times 3. We can use the formula phi of mn equals phi of m multiplied by phi of n. We have phi of 21 equals phi of 7 times 3. Then phi of 7 times phi of 3, which is from rule number 3. Then 7 minus 1 times 3 minus 1 from rule number 1. And we have the answer of 12. Therefore, the phi of 21 is 12. Rule number 4. If the prime factorization of n is given by n equals p sub 1, p sub 2 until p sub k, then phi of n is equal to n times 1 minus 1 over p sub 1 times 1 minus 1 over p sub 2 multiplied until 1 minus 1 over p sub k. Let's solve for the phi of 600. The prime factors of 600 are 2, 3, and 5. Substitute the prime factors to the formula. We have phi of 600 equals 600 times 1 minus 1 over 2 times 1 minus 1 over 3 times 1 minus 1 over 5, and it is equal to 160. Therefore, the phi of 600 is 160. Let's go back in Euler's theorem. Let n be a positive integer, and let a be an integer that is relatively prime to n. Then a raised to phi of n is congruent to 1 modulo n, where phi of n is the Euler's Theorem function, which counts the number of positive integers less than or equal to m, which are relatively prime to n. Let n equals to 12, and for all a is less than n. We have the solution. A is equal to 1, 5, 7, and 11, and phi of 12 is equal to 4. So a raised to 4 is congruent to 1 modulo 12. 1 raised to 4 is congruent to 1 modulo 12. 5 raised to 4 is congruent to 625 modulo 12. 7 raised to 4 is congruent to 2401 modulo 12. 11 raised to 4 is congruent to 14,641 modulo 12. That is the end of our discussion, and I hope you learned something from me. Again, I am ArjinelR Caballero. Have a great day, everyone.